Can everybody hear me in the back? It's working good? All right. So, yes, my name is Charles Doutriaux. I work at Lawrence Livermore National Laboratory, and this is PyData San Francisco, it's August 14, 2016. And I'm going to talk about, you can, oh, may I take it out? Breaking everything, no? Can you hear me better like that? No? Okay. No, they can't hear me. Just this one. Is it better, this one? Okay, perfect. All right. So let's start over. So my name is Charles Doutriaux, and I work at Lawrence Livermore National Lab. Oh, no, maybe not. Still works there.
I want you to hold that the whole time. Right, pop it in there. It's more sensitive.
Oh. It's okay, I can hold it. I don't mind. All right. And so I'm going to talk about this new project we're having, which is Virtual Laboratories, which is a vision for Earth science, collaborative and distributed environment, virtual labs. And so I put a few names of my team at Livermore, but that's a really, really big project that's been going on for a lot of time. It's a multi-agencies, it's international, and it's a mix of universities, labs, private sectors, everything. There's about 30 logos here, and I probably forgot a bunch of them. Just had to cramp as much as possible in there. So it's a project's been going on for, I'm going to show in my historical notes, it's been going on for a long time, so I will go over, try to give you the background, because I don't think there's many people here in the field. And then I'll talk about the ultra-scale visualization climate data analysis tools, which is more like on compute part, and talk about the Earth System Grid Federation, which is a data center, sort of trying to give you the nitty-gritty, and then I go on about fusing all that and creating our virtual laboratory. So a brief story about PCMDI, which is a program for climate model data analysis and intercomparison, which is almost an acronym that needs an acronym, PCMDI. It's been created in, we have to go back in about 1989, and at the time there was a bunch of already climate model centers running all over the world, but they were all basically living in isolation, doing their own model, and they all claimed they were the best in the world, and they were very good at what they were doing, but each model was more centered about looking at different aspects of science that they were interested in, so they were really good at that. So in '89, the DOE, Department of Energy, created this kind of independent arbiter, just to try to get the scientific community together and evaluate this model, because at the time, it wasn't very hot yet, but they decided to realize that this global warming thing, well, maybe was something we should look into, so we should know how good these models are to predict these things. So that was the whole idea, and PCMDI was created, and it was just to evaluate the models, but we didn't have any models, so that was, we could be completely objective, because we're okay, we're just going to look at you guys and try to tell you, what you can do better. And it was a joint effort between research scientists, so actually scientists, from the science point of view, and computer scientists. It was actually a 2-to-1, two computer scientists for each scientist at the time. So to help the scientists focus on the science, and the computer scientists to give them the tool to do what they needed to do their research. So that was nice. And so a few years later, take a time, coordinate all these people, and that led to the first ever international global atmospheric model intercomparison project, which basically was, we told everybody, okay, you all have your greatest model ever. We're going to ask you, we're going to give you the initial set of boundary conditions, which is the sea surface temperature, for about 10 years, and you're all going to run your model with the same kind of input, because everybody has their own Turing's. So everybody's going to run the same thing, run it for 10 years, and then we're just going to look. Believe it or not, it was really hard to actually get them to do that, convince the people to just work together, because everybody was kind of scared about the whole great, but they were like, yeah, I don't know, I really want to compare and stuff. So, and we sort of, we looked out, I think, in the end. I mean, they looked out, I wasn't working there yet. Turns out that we discovered this common cold bias across all the models, so which is basically around 200 hectopascal kind of in atmosphere. There's really cold, all the models were way, way, way too cold compared to observations. And everybody knew that, every model, they're yeah, we suck there, that's okay. So, we're so good at everything else. And then this thing came out, and they were like, oh my God, it's everybody, actually, nobody can do that. So they realized there was actually a fundamental issue. It was just their model, it was every model. So there's some parameterization, something that was wrong. And that was actually our draw of luck for us, because that turned out like everybody got super excited because the model got so much better from that, and realizing like, oh, there's actually some value to collaborate. This is not just going to be a ranking operation, it's just going to really help us make better model and find, the things. So we looked out on that, and that made things much easier in the future to get people to go into the project, because now they knew like there was some actual value to that. I'll do a quick digression about model development, just for the thing. And at the origin of atmospheric climate model, that was pretty much like this kind of thing was really done to just simulating the Adler Celsius, basically the air rise and drops down around 30 degrees, which is why you have like it's dry, and that's why you have most of the desert and the planet are there. And that was really bare bone, basics, some little equations. And then, as computer get better, the scientists get better, and we're like, hey, add more parameterization, and there's like, this is kind of a typical now atmospheric model. So you introduce, aerosol and clouds and ozone, and you have your input and output of energy and the greenhouse gas and all that, and how much the ground is absorbing heat, things like that. And then it goes even more crazy, because now you don't just look just at the atmosphere, like, well, the ocean is very important, and then you have chemistry in the ocean, chemistry in the atmosphere, you have precipitation, and you have runoff model, and ice sheet models, and all kind of model, and it's all like together, and that's what we call coupled model. So it's like thousands and thousands of different physics equations put together, modelization. And so these models are run at some very specialized centers with a lot of, obviously, computer power. So that's just to give you an idea. So EMIP was super success. So we had EMIP 2, and then people are like, okay, that's cool. So now we all like have an idea of what these models are. But again, we're here like to try to think about, global warming and climate in the future. So like, is this model actually good at? I mean, maybe they're really good at simulating the climate now, but can they actually? How do they behave in a totally different environment? So there's been simulation like PMIP, which is Paleoclimate Model Intercomparison Project. And we use basically ice cores and trees and things like that to figure out the climate of the last glacial maximum, about 20,000 years ago, where the climate was really different. And we try to run the model in these conditions. So that gives us more information. And so a lot of these MIP started to create together, just to evaluate the model, because that was very important. Like, we want to know why these models, how good they are, and are they like stable. So now the couple models, they do this crazy thing I showed earlier, which have ocean, sea ice, land, ozone, chemistry, ocean chemistry, everything together. And that led to the Intergovernmental Panel on Climate Change, Assessment Report 5, which leads to treaties such as the Kyoto Treaty, which lead to policymakers being able to actually do informed decisions. So it's really important to get the model right. And now we're in preparation for CMIP 6, because this assessment happens every like 6-7 years. Basically state of the art of the science in Earth. So, not to say there was like a lot of lesson learned during that about 20-30 years odyssey, I guess. So, like, for example, for the first project, EMIP, there was some data that we just could never even read. Like, they sent us a binary thing, and we just couldn't look at it, we couldn't read it. They sent us even the code, we couldn't compile the code and stuff. So, second round, we're like, okay, we're going to give you some tools to rewrite the data, so at least we'll be able to read them back in. And so as this process go around and get better, we have all our set of tools in-house for our scientists, which has been more and more democratized and being used across the community. So that's where CDAT, or Climate Data Analysis tool set, was created around the line, and set of tools so for Earth scientists, basically. Then the CMIP came, and we realized that we had to have some convention because everybody had different data, and we adopted NumPy, and we created the Earth System Grid, to which I will come back later. But now I'm going to talk so about UVCDAT, which is Ultra-Scale Visualization Climate Data Analysis Tools. And that's basically our analysis stack. Like, kind of think of it as, I don't know, maybe like the NumFocus of Earth science or something like that. So it was, as I mentioned, born from our in-house set of tools, and around 96, which is when I started to work there, we decided to use Python as our glue for all these tools, because Python is awesome, we know that. It's really, really good, actually, at talking to C and all these other languages. So we do that, and we have all these tools now to analyze and visualize like big climate model simulations and also observations. And it's mainly 4 DOE labs, NASA, NOAA, 2 universities, and 2 private companies that work on the core. And what's the core of UVC? The core UVC consists of basically numerics, which is obviously NumPy. If you're in Python, you're going to use NumPy. And we have CDMS, which is a climate data management system, which is doing all the IOs. And we have our in-house, like really custom tools for scientists, which is climate data utilities and GenUtil, which are more generalized utilities for just manipulating arrays kind of things. And we have VCS, which is a visual control system to do geo-based data. So to go down just on NumPy and a little digression on that, okay, it's great. We have all this data, so we're like, okay, let's just use NumPy, because we start to try to implement our own, math operators and stuff, and it started to suck so much of our time just to implement that. We're like, look, this thing called NumPy is here. Actually, it was numeric. We used before NumPy existed, but then we switched it to NumPy. And NumPy is great. It's awesome. It's really fast. And we had the talk from James Powell earlier explaining you why you should use it. So it's great, but for us, it's just not quite enough NumPy itself, because we are we're using actual real-world data, not just the model. We're comparing to the observations. And if you say observations, you mean missing data, because like your instruments died for like 2 weeks, and somebody had to go and implement it and stuff. So we needed, and NumPy came with MA, which is awesome for us, which is mask array. So like, okay, now we know how to deal with arrays where there's no data. NumPy does that for us, so that's good. But that's still not enough, because what you have out of NumPy and MA is just numbers. I mean, it's an array. It's just a bunch of numbers, and that's great. But if you want to do like a software suite, and that's really like our strength in our software, is like we try to integrate all our tools and make them work together. Okay, I have numbers, and what can I do with that? I mean, it's, I'm just going to give it to my next set of suite, and it's like, I don't know, give me numbers. What do you want me to do with it? But we introduced these notions of metadata and dimensional information that are associated with the data. So that's what we call our mask variable. And a variable, as in addition to just the numbers, we give them domain information. So for example, it's a 3D array, and dimension 1 is latitude, dimension 2 is longitude, and we also have vertical informations. So now, like, if I pass that to my next part of my suite, it's like, oh, okay, it's actually like Earth kind of data. I can plot that. I can do things for you automatically. I can, project it on the globe, or do a subset, based on your region, things like that. So you're already a little bit further, but you still need more. Like, what is it? Okay, it's geodata, and I'm going to look at it. It's like, oh, it's probably a temperature, but temperature of what? Or so we have all this notion of metadata, and that's like super important. I'm going to try to hammer that. The metadata is probably the most important part. It's like documentation of what it is you're plotting, and that enables your software to make a lot of very smart decisions for the scientists. Really helps them to do the right thing, and helps the scientists focus on the science and much less on the data cleaning and things like that. So the metadata gives you the units, it gives you the name, it tells you, which experiment is coming from, which model has been running that. A lot of things that you can actually help your software to do the science really smart. So because we have the metadata, now we could develop a much better climate data management system, which is IO. And that allows us to do smart tools, because we have all these models. They all come, at different resolution, depending on the computation power of the center they're running at. And so some models are like, I don't know, like 20 by 20 data, and some are like 200 by 200, like very high resolution, or like 360 by 180 if you run at the degree, even worse now. And so you want to get your data and look at them over the same area of the world, and now we can just say, okay, read me, open that file, and read me the clouds, and I just am interested, like, in the tropics, like -20 to 20 or -30 to 30. And yes, I would like, to have from 0 to 360 and not from -180 to 180, because everybody stores it differently. And oh, yes, I'm only interested in these 3 years here. And because the metadata are in the file, and the file is basically self-documented, we can do that in one line, like as you see here. I just say, okay, I want this area. And that takes, if you don't have this metadata, it's going to take you a lot of line of codes, and it's going to make your code super not general, like, oh, if model A get index, 1 to 20 for the time, but if it's model 2, because this one has more data, get it a little bit earlier and run it later, things like that. So it was basically all these tools that are really helping the scientists to do I/O easily, and help you again focus on just what it is you need. Then, okay, you've got your data in, and so we have all these packages, which is climate data utilities and generic utilities data. And because we were working hand in hand with the scientists, we could develop all these things. A lot of specific tools, like changing units, creating departures, basic stack basically for them. Doing regridding, because it's not that easy to go from a curvilinear grid to a rectilinear grid, because they all have different resolution, as I say. So if you want to do difference, you need to make sure like they both basically align and match together. Vertical interpolation, and then again, all of I/O have using these conventions. So we rewrite it, we can use it in another package. It will have all the history and the provenance and all these things designed with you. So you did your analysis now using these tools, and now we have the visualization control system, VCS, which gives you publication quality output. And it's really like targeted for like earth science again. And as you can see here, in like 5 lines of code, you can actually read in your data and plot them on, and you will know it's Earth, which is not necessarily easy to do in other packages, just like Matplotlib. So all that was nice. Our biggest challenge for the longest time was, okay, we're using Python and it's great, and we've kind of convinced people to use Python, but distributing that thing was just hell, because there were like 300 megabytes of sources to compile. And I had to work on every machine. And I don't have my token here, but I have pretty much like that much keychain of tokens of machine I can log in, just because for the longest time, 50% of my job was just to go install that on the supercomputers for everybody. And everybody was like, hey, I love your software, it's great, but it's just, I can't use it because it's going to take me, 6 months for interaction with you to get it on a system, which is not really true, but that was our reputation. And so thank you very much to Conda. Like, I cannot thank them enough ever. They made my life so much easier. And now in one line, I can just say, like, go get data, install our software, and people can use it. And so that was good, because now we really have the full power of Python, which people are convinced by now. Like, everybody agrees that Python is great. But they were always complaining that, like, well, I have to install your Python, but I'm already using Matplotlib, and I'm using, RPy and all these things, and you don't come with it because it was too hard to install already with all the software we had. So we do distribute with Matplotlib. That's the elephant in the room, because everybody's using that here. And we're giving like pi tables, all these things. Now you can do it. So we have basically a really good ecosystem. And the strength of this ecosystem is that really all of the tools that we develop, they really work nicely together. So you can go, like the scientists can really go from reading in the data to analyzing them, plotting them, and saving them. And it all works together nicely. And I was really, really happy to listen to like James Powell's talk on, I think it was on this tutorial on Friday, when he mentioned that NumFocus is really trying to get this direction now, but they're trying to get all the tools to really work better together and like with less friction when you go from one tool to another. So I think it's really excellent. I'm really happy about that. Because that's always, you jump and your data are not quite ready for the next step and you have more post-processing. Anyway, that takes us to the second set of tools that we're distributing, which is Earth System Grid Federation. So as I mentioned, most of these tools have been developed in the context of analyzing model data. And with each iteration and more power from the computers, and all, especially the supercomputers, the labs are very happy to have bigger and bigger computers. And the scientists are like, oh, more power, yeah, I can just double my resolution of my data, even though sometimes it doesn't make any sense physically anymore because some assumptions are not true. But anyway, we have more and more data. We have about 2 orders of magnitude with more of data with every iteration of the project. So very quickly, like originally we used to just basically host the data and have people download them. For AR5, the last process, we realized that like, no, there's no way we can host in-house. We don't have, even though we're like a DOE lab and we have a lot of like pretty much unlimited hardware and computers we want, we just can't hold that much data and have everybody come and hiring. And for the next iteration, it will be even worse. Not only we can't hold it as an institution, we can't, like it's going to take too long for people to even download them. So the problem of distribution of the data, that's been done by the Earth System Grid. And what we decided to do was like, well, it's just too big. So let's keep the data, let's serve the data from where they are generated, basically. So we created this federation of data nodes where you generate your data. and you just open it to the world with authentication, of course, and things like that. So now we don't have to go constantly bring everything to the one single institution. There was a core set of sub-data that was analyzed, like identified for ER5, and this core set was replicated at a few centers. But in general, most of the data stayed where they were produced. So what's a node look like? A node look like a node manager, and a compute node, and a data node, which has the data and an index. And so all these nodes talk together. So now we have a single point of entry for the user. It just looks like a big fat cloud, basically. We just have reinvented like a federated cloud of lots of data. And people can query, download, visualize the data they want. And we also do data aggregation because this file are cut in different chunks. So it looks like one big data set. And we have user notification service because it's still like there's always case where you download this data and then a year later somebody found a bug in the simulation. So like, oh, we need to update the simulation, something didn't go work in the post process. So then we get the user like, oh, by the way, you might want to rerun your thing because this data have been updated, cleaned up a bit, or maybe there's more data available to you now that's been processed. So that led to things like quality control. And we have 3 levels of quality control. We have level 1, which is like you produce your data, you think it's good enough to be distributed to the world. So that's quality level control 1. And then when we're going to replicate this data, go to the primary center. So your data has been identified as like core valuable. We have more checks. It goes to the quality centers. And then when you go to the publication level agency, which is level 3, even more screening on the data, then you get a DOI, so you can use it in your research, and it's very important because the DOI is important because it takes a lot of resources to produce this data. I mean, a lot of computers and a lot of time and a lot of hardware. So they like to get credit for people using their data. So now it's codable, and it shows that, oh wow, a lot of people are actually using this data. That wasn't completely a waste of money. Thank you, sponsors. So it's Earth System Grid is a really big project. There's like, I just listed here about 18 subgroups, and we deal with every part of the life of the data, from publishing it. We deal also with security and resource allocations, quality control, replication. I mean, there's like a lot. It's a really big system. So where it goes to, and I kind of hinted to that, the Earth System Grid is, okay, in the last instance, we already realized we couldn't host everything in a single institution anymore. But now it's worse, but it's to the point that like, even if it's distributed, it's going to be so big for CMIP 6 that if you're a scientist and you're like, oh, I want to look at like, 3 or 4 different variables and I'm just going to run my classic analysis on it, it's probably going to take about, if you just do the normal standard model of downloading it, even to your institution, assuming your institution can hold that much data, probably like a year or 2 worth of data, and you're pretty much out of a job by the time of, your PhD is going to be 10 years now, so you can do your PhD. So what we need to do, we need to move out of this concept of getting the people to remember that you don't download the data and get them used to, let's bring the code to the data, because we want very little movement data. So that's where we are. So that brings us to this new project. Oh, sorry, you want it back? I'll put it back for you for a minute. All right. Okay, so that brings us to the Virtual Laboratories, which is, because we have a hand in these 2 projects, and we are the core of both of them, we're like, well, we really have these 2 great things, just make it like really work together. Now we have the code, we have the data, let's just create this virtual environment so the scientists can actually work with this data, because there's so much value to it. And that leads us to the compute working team. And so, as I mentioned, we're going to bring the code there. And our goal is to basically get the code to the data, where the data is at, using clusters or extreme scale, basically an extreme distributed data archive with computing centers. We're going to use CDAT, which is actually being renamed the Community Data Analysis Tools now, because we're really broadening to out of just earth sciences. We're trying to reach out to bio and things like that. And we had a talk yesterday about flu, and you can really link these 2 kind of data, flu and weather and things like that. So it's now the community. But anyway, it's going to be basically the core, like to run the computation on the server side. We're hoping to, but we went for an extension of web process services to do our API. So that was the first part. We have this API which is really language agnostic. We just wanted to know, okay, let's give a way for people to tell, like, I'm interested in studying this data and do that. So it's completely agnostic of whatever backend implementation you want. It's just we added a few things that we need for our data. You're going to do it and implement it on the server side. And we also, of course, because it's web processing, you end up with like Eart, which are about that big and that long, if you like 20 data sets and things. So we have Python user end API as well, so you can just script it and command line it and things like that. So that part is pretty much done as far as the API goes. We're pretty happy with our version 1 of the API. And we have, of course, more iteration coming in the futures. And the next part, like really coming up now, is the implementation of the server backend. We have various things, and there's so much we want to do. Like, first of all, we want to have different ways to implement the same kind of algorithm, because there's, we here at PyData and we see there's always new techniques and new things going on. So we want to be, able to use all these techniques. We can, be it like MPI or Ophidia, this project in Italy, or Spark, or whatever it is. You can implement it different ways and let the user decide which way they would like. We want the API to still work, so that part's pretty good. But we also need to leverage from the rest of the Earth System Grid Federation teams. Like, we don't want to reinvent authentication, security, data allocations and things like that. Now, in the future, like the really exciting part, at least to me, for the server side, is to do all this auto-smartness about like where to run the code, because it's nice to bring the code to the data, but since the data is distributed everywhere, like, where do we really send the code to? Because data may be at 2 different centers, and like one is like a super fast computer, and you're like, oh yeah, I should run it there because it's going to run my simulation in like 15 minutes. But hey, it turns out like, oh, you're in the queue and you're not going to run for another 2 days. But like this other center, oh, yeah, maybe it will take like 3 hours to run, but hey, I'm first in the queue, so maybe we should run it there and download the data back, and it will still be faster than waiting for this super fast computer to let me go in the queue. So that all these kind of like machine learnings and things like that are really exciting that we're going to do. And it's basically starting now. And on the other hand, it's like, okay, so now we have the distributed data, we have the server-side computation, but we still need the scientists to work together and be able to do the analysis easily. So we have this vision for VCDAT, which is basically a window on top of this computer server. And it's very similar, like, as I was like looking at it, and I really think it's something kind of like Jupyter Labs, where you can come in, call your data, look at your data, do further analysis locally. Hopefully it can be collaborative too. That's what we're hoping to. So like scientists in, like here, can also work with scientists in Germany or scientists in Australia. They can all work together, see what each other are seeing, and work together. It will help us also with provenance and openness and reproducibility, because it's a very, like now climate change is very political. So you need to make sure like you're super clear, super clean, like everything is here and reproducible, so nobody can attack you. So that project is also just coming up to speed, like the VCDAT thing. So as a summary, we have years and years and years of tools investment in the domain. We have 2 strong systems, I think, for data distribution and data analysis that are finally getting together and being integrated. It's open source, all of it, completely open source. It's easy to grow and add on it. It's very early in the process, so like if you're excited about any kind of these things, we'd love to have more people join to contribute. We're expanding beyond the herb sciences. We're just trying, like I said, bio, maybe other fields as well. Always looking for feedback from the community, like why do you use that? Why don't you use these new things? That's also why I go to the conference to learn about what else we should do. Okay, that slide is more like for later when you go download it, so you can go look at all this thing we're doing. And that's about it. Just ready to take your questions now. Thank you.
Questions? So some of the new models use unstructured grids compared to a
Yes.
lot of the structured grids. Does that present any challenges for you? So like integrating impasse, for instance, into your frameworks?
Yes, it does present a lot of. So the question was like about the new type of grids, like, and CMIP6 will have a lot of that, unstructured grids or things like that. And yes, it presents challenges, but we have tools to, at least a regrider for now, as a first thing. But let us go from any grid to any grid. Like we use the Earth System Modeling Framework, regrider, and that lets you do, that's our first solution, but we're trying to re-implement tools as well to work as much as possible directly on the native grids. But these tools are coming out slowly. Most of them come from the ocean community because they've been dealing with these weird grids for a long time. So we're getting the tools from them as well and bring them in. Yeah.
Okay, if there are no more questions, thank you. Thanks, Charles.
Thanks.
Great talk.